Hi guys, in this video we're going to look at aromatic compounds, Kekulé's model of benzene, benzene's resistance to addition reactions, the hydrogenation of benzene, bond length in benzene, then we'll finally look at a more accurate picture of benzene than the Kekulé model before summarising.
Before we talk specifically about benzene and its structure, we're going to talk more generally about aromatic compounds, which is a term you should have met before. The aromatic compounds get their name because they tend to have strong smells. They come from the same root as the word aroma, which refers to usually pleasant smells. Aromatic compounds are compounds that contain at least one benzene ring. A benzene ring is shown here. All of the compounds you've met before which don't have benzene rings in them, so for example the alkanes, the alkenes, carboxylic acids, we refer to these as aliphatic. What we're saying here is they just don't have an aromatic ring in them. So now let's look in more detail at the bonding structure within a benzene ring. We've known that benzene exists, and with the structure C6H6, since the 1850s, but it took a much longer time to work out the structure because it's unlike most other molecules that the scientists of the time had come across. One successful model of the way that benzene is put together was put forward by Auguste Kekulé in 1865, around 15 years after we first knew that benzene existed. He suggested it was made from a 6-membered carbon ring, so 6 carbons looping round to connect in a ring. This structure, he suggested, had alternating double bonds, so one carbon to the next would have a single bond, then a double bond, then a single bond, and so on round the ring. 3 double and 3 single in total, which we can show in skeletal structure here. The reasons he suggested this structure is because of the number of isomers that we get from benzene if we add groups to it. Experimentally, it could be seen that if we added one group to benzene, then you only get one isomer. This is consistent with the structure that Kekulé put forward, because if we were to add in a group here, which we'll call X, to replace a hydrogen, then you could just rotate this structure and it wouldn't matter which carbon, whether it's here, 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 or all the way around, you put it on, because they're all equivalent because of the symmetry of the molecule. So there's only one isomer here, which matches up to the experimental findings. It was also found that if we added 2 groups to benzene to replace the hydrogens, we get 3 isomers. So remember, hydrogens aren't shown on these skeletal formulas, but each one of the 6 carbons does have a hydrogen coming from it, which we can then replace by another type of species. If we added 2 of these species onto the benzene ring, with Kekulé's structure, we do indeed have 3 options. With the symmetry, they can either be no carbons apart, so they're right next to each other, or the 2 species that we add can be separated by 1 carbon. Finally, the 2 species we add could be separated by 2 carbons. If we continued to move this other one round, so for example, if instead of putting it here, we put the species on this side, this is the same as what we had before, just flipped over. These are the only 3 different isomers you can make from Kekulé's structure, and this matches up with the fact that only 3 are found experimentally. While it was a good model, Kekulé's model of benzene is not what we work from today. There are 3 main failings of the Kekulé model which will help lead to the current and more accurate picture of what benzene actually is. The Kekulé model makes benzene look like a cyclic alkene with alternating double bonds, so we'd expect it to undergo similar reactions to the alkenes. Alkenes will readily undergo addition reactions where the double bond will open, become a single bond, and accept two more species onto each of the carbons. Benzene resists these reactions and is far more likely to undergo substitution, where we remove a carbon from the benzene and add on a chlorine atom. Kekulé tried to explain this difference and defend his model by suggesting that the double bonds in the alkene rapidly swap. So we go from having the structure shown on the left, where the double bonds in the ring are here, here, and here, to the double bonds switching positions to the other three in the benzene ring. This would form an equilibrium that's very fast moving, and because the double bonds are constantly moving position, this would make addition reactions, like we see in alkenes, difficult. Unfortunately for Kekulé and his model, even though he'd explained the problem with addition, a second problem does arise. With the Kekulé model of benzene, when we look at energy changes that it undergoes during hydrogenation, we find something that doesn't make sense with the model he put forward. Hydrogenation is the term we use when we add hydrogen into a double bond. This is a common thing to do with alkenes, and we can see the example with cycloalkenes below. So we have cyclohexene here with a double bond between this carbon and this carbon. We react this with hydrogen to form a cyclic alkane that is saturated. It has no double bonds. The enthalpy change that goes along with this is minus 120 kilojoules per mole. This is the same if we were to have a double bond here or here, because these three molecules are in fact all the same and just rotated, so when we add hydrogen into any of these positions, each time the enthalpy change will be minus 120 kilojoules per mole. Now, if the Kekulé model is correct, we could just combine each of these three steps shown here, where we hydrogenate this double bond, and this double bond, and that should be the same, energy speaking, as hydrogenating all of the three double bonds in benzene. Because the Kekulé model just shows benzene as a combination of all the above cycloalkenes into a triene. So, for example, if Kekulé's model held up, then we would have the three enthalpy changes from above at minus 120 kilojoules per mole, and the total enthalpy change should be found at minus 360 kilojoules per mole. This is not the case when we carry out the experiment. When we add hydrogen into the actual structure of benzene experimentally, the enthalpy change we get is in fact only minus 208 kilojoules per mole. Less energy is given out compared to the expected 360 kilojoules per mole. This mismatch shows more evidence that the bonding in benzene is not exactly as Kekulé predicts. This video is getting a bit long, guys, so we're going to split it into a couple of parts, and I'll see you in the next one.
Hey guys, I hope you enjoyed the video. If you're looking for an amazing A-level chemistry resource, join me today in my series of engaging bite-sized video tutorials. Just click the snap revise smiley face, and together, let's make A-level chemistry a walk in the park.